All right, welcome to a new segment I call What's in a Lab? So, we're going to talk about the debriefing of the first real physics lab, or I should say one of the physics labs because I changed my order of operations. But this is the one where we had the constant velocity car. Okay, so this is going to be a discussion about the constant velocity. That's not a Y. That's not a Y. That's not a Y at all. There we go. Constant velocity car. Okay, which I didn't call it the constant velocity car, but that's actually what they're sold on. If you check out Amazon.com, it'll just, you type that in, boom, there's our cars. So we're going to talk about how do you get to your final physics equation, and most importantly, what's the logic and what's the reasoning behind it. All right, so I'm going to just set up a scenario. So I'm going to say that I've got a number line out in the hallway. Okay, here's 0. And I'm going to say that my car started at 3 meters, okay? And then my car went this way, okay? And I don't know where the heck I ended up. Let's see, 8. Should probably get 8 good data points. Let's just say I ended up at -9, maybe. Something like that. Okay, so that's where I ended up. So that's what happened. So I started here. This is my initial start. And this is where I end up. So finish. So when I make my data table, okay, and then I plot my graph, remember, the purpose was to graphically and mathematically model the relationship between position and time. So I want to know what is the exact relationship between the position the car was at and the time the car was there. Okay, at no point am I talking about distances. Very common. Students want to start throwing out distances. They want to talk about that. We're not talking about it. We're talking about a more fundamental level. Where is the car and when was it there? It's like you're trying to solve a murder mystery. It's like, oh, at what time was he seen here? You don't ask, how far did he go to get here? I don't know. I don't know where he started. I just know where he was. All right, so when I make my graph, I'm going to put position on the y-axis. All right, and hopefully did this in meters. And then you've got time on the x-axis, and so we do that in seconds. So now if I did this, theoretically, if I did this correctly, I should have started up here. All right, and of course I should have thought this all the way through, but I didn't. So, well, doot. And I will go basically somewhere down here. Okay, that's the way my graph should look, where this is 0. Because I ended up somewhere -9. No, this is not to scale. But theoretically, if I trace my data back, I should have started somewhere around 3, right? I mean, at time 0, theoretically, that's where I put my car down. Okay, so I should have a graph that looks like this. And then if I break this down to, what the computer gave me, let's say the computer gave me this. Let's say give me y equals -0.41 meters per second times time. I'll use y's and x's for now. Boop. X plus 3.02. And that'd be meters. So let's say that's the equation it gave me. So we got to break this down and figure what the heck this is talking about. So first of all, I'm going to bust out a different color here. Let's go school colors. Purple. All right, so I'm going to take this, and I'm going to bring it, and I'm going to work over here. So remember, we don't want to see y's and x's. We want to see the actual, concepts. So really what I have is I have position equals that -0.41 meters per second times time plus 3.02 meters. So that's the actual equation. That's my mathematical model. All right, so here's my graphical model, and here's my mathematical model. So now I want to see, well, okay, what does this stuff mean? Because once you have that, you ask yourself, what does the y-intercept mean? What does the slope mean? So when I'm looking at the meaning, and I'll go blue, if I go the y-intercept, because I like to start with that one. All right, what does the intercept mean? Well, again, it's always what y is when x is 0. So in this case, it's going to be what my position is. Position is when time is 0. Okay, so you got to think about that. Okay, so it's basically where the car was when time started. So I'm going to call this my initial position. Now you could have called it your starting position or whatever, your starting location. That's all fine. But in physics, we use the words initial position. And the evidence for this, that's my logic, but my evidence for this is the fact that I said I started at 3, and if I look at my numbers, I've got basically 3 as that y-intercept. And also if I look at the units, position would be, you know, where are you? So that would be a distance type thing. It's meters. And again, I have units of meters in my number value. So therefore, I do have evidence. I've got numerical evidence to support that statement. So that's why I believe this is my initial position. Now, when it goes to the slope, this one is more complicated and also more simple at the same time in a way. So if I look at my slope, this is, again, it's something that was constant. It's something that was constant. It also has to do with the rate of change. So this was something that was constant and often a rate of change. Or it's something that relates these two variables to each other in a uniform way. So in this case, we've got our units of meters per second. So our units are meters per second, which if you think about it, that's almost the exact same, it's not the same units, but it's the exact same idea as miles per hour, which we call mph here in the States. So you can ask yourself, man, where have I ever seen something like this? Something like this. Okay, well, those are kind of units of speed, you know? And if we ask ourselves, a lot of the opening statements before we did this lab was that a car was traveling at a constant speed. That was a lot of people's hypotheses. So if speed is constant, that would meet this idea of slope being constant. And if we look at the units, well, those are units of speed. All right, it's a rate of change. It's definitely telling us our position's changing relative to time. So in reality, what the slope means is it seems like it means speed. All right. But it's not actually speed, because if I look at my data, there's a negative sign here. I have never been in a car and traveled at a certain speed and said on my speedometer, oh look, it's going negative. Because speed doesn't care about direction. It doesn't care which way you're going, so there can't be a negative when it comes to speed. So where the heck is this negative coming from? Well, let's look back here. We're going in this direction. We are heading in the negative direction. So not only does this tell us speed, but this number, this plus or minus, is also telling us direction. The groups that had positive slopes, they all went to the right. The groups that all had negative slopes, they all went to the left. So this is telling us not just how fast we're going by the numeric value. This is telling us which way we're going based on the plus or minus. And this idea of speed and direction has a very special name, and we call it velocity. And that is the true meaning of the slope. Okay, so speed's close. It's close, but it's not the whole story. Because what this means is that this number not only tells me how fast I'm going based on the number, it tells me which direction I'm heading on based on its positive or negative. If it was purely speed, we couldn't have any negatives, because speed doesn't care which way you're going. It just asks, how fast are you going? So what that leaves me with is, let's go green. Go green, yeah. So what that leaves us is our final equation. So we're going to take this guy, all right, take this, and we're gonna go down here. We got some space still. And so now I have a new equation of position equals, this number is going to be replaced by the idea of velocity, times time, let's keep in parentheses, times time. Oh no, I ran out of space. Okay, so this is shady here. Plus, this is why color's good, initial position. Again, notice how all my concepts are just one or two words. If you ever can't think of a concept, you're like, what does this mean? You've got like a whole freaking sentence. You got to try and pare it down to one or two words you've probably heard before in your life. So this is perfect. It's awesome, except there's one major flaw. That is long. I do not want to write that my whole life, okay? So in physics, we replace all these with symbols. The symbol for position is very famous. Pirates have been using it forever. It's X. All right, X marks the spot. It means position. Symbol for velocity is, yes, you guessed, it's a V. Symbol for T is, as you obviously know, that's a little T there. And then initial position, well, that's a position as well, so it has to be an X. But in physics, the way we show that something's a starting or an initial is we use this little subscript 0 down here, sub naught. So it is the initial or the baseline position. So this is the actual physics equation that we will be using in class over and over and over again. Now, some might be looking this up, and you Google it and things like that, and you might end up with an equation that looks a little bit like this, where you say, oh, sorry, that's not, why am I, just there we go, erase, yay! You might end up with velocity equals delta x over delta t. Well, this delta x here means displacement. All right, and these delta literally means change in. So your velocity is your change in position over your change in time, which, remember, is the slope. So your slope is velocity, which is your change in x, because that's on the x-axis, because I can never replace position with the letter x, and then times a t, so divided by change in time. So therefore you get that equals a v. So that's where that equation comes from. But fundamentally, the one you need to understand is this guy here. That's when you got to fundamentally understand. So highlight that. You got to fundamentally understand that one, and you will see us use this one in class as well. But it's an understanding of what the slope actually tells you. All right, so that's kind of our debriefing. So if you missed anything during the class discussion, watch this again. If you want to prep for something, hope that was not too boring. I mean, I know it's riveting stuff, but that's basically what we need to walk away with, this idea from the constant velocity car. And now I'm just enjoying highlighting stuff for no apparent reason. Smiles. That guy's really happy. All right, I'll see you next time. Enjoy science.